And tonight we've got actually two speakers for you. We're looking forward to. So first one is Ella Davis, and she's from Virginia Tech, Department of Geosciences, and she's talking on the tectonic transport directions and timing of metamorphism in the southern part of the Northern Highlands terrain in Scotland, of course. So Ella's a second-year master's student at Department of Geosciences in Virginia Tech, where her undergraduate research focuses on quartz microstructures from samples collected in northwestern Scotland under the direction of Dr. Richard Law. This led to further research to determine tectonic transport directions and deformation environments using small-scale shear structures and quartz fabrics. So after Ella has spoken, we're going to have Kiara. So Kiara Brooksby is from the Camborne School of Mines at Exeter University, and her talk is on paragenic evolution of tin-dominated lode systems in the Pool mining district of Cornwall. So Kiara obtained her Geology Earth Science BSc in the University of Glasgow, so she's a Glasgow student, in 2019 before moving to the University of Exeter, where she's a Richard Osman, not the one who does, no, anyway, scholar. She obtained an MSc in mining geology. In 2021, she began her current PhD research at the Camborne School of Mines in Exeter University. Both of those students have received grants from the Society, and as part of their grants, receiving grants, they've both been asked to give a wee talk, a presentation on what they got the grant for. So first I'll introduce Ella to you, and she's going to be talking on the tectonic transport directions and timing of metamorphism in the southern part of the Northern Highlands terrain. Ella, it's over to you.
Whoa. All right, I'm gonna share my screen and hopefully this works. Okay. All right. Can you see like the normal presentation screen?
Perfect.
All right. So, like she said, I'm going to talk to you guys about the tectonic transport directions and then also a little bit about the timing up in a terrain which is called the Northern Highlands terrain, a bit north of you guys. Okay, so just to kind of do a little bit of background, I am looking and researching the Caledonian Mountains. The Caledonian mountain chain is a really large, really old mountain chain that extends from Greenland and Scandinavia through the UK and Ireland and all the way down to the eastern coast of North America. Like I'm in Virginia right now. I'm sitting in the Appalachians. This is the southernmost extent of that mountain chain. I, of course, am researching an area in Scotland, which is just one little bit of that mountain chain. But in order to figure out the history of an entire mountain chain, we have to kind of do smaller studies and then piece them together. And what we mostly focus on here is looking at tectonic transport directions, how rocks got deformed, and then when the mountains were being pushed together, which way things were pushing. And then we also look at timing of metamorphism. So when were the rocks actually being pushed together? When were things growing, or things as in minerals? And then can we get an age range of when this was happening and figure out, okay, in the context of the entire mountain belt, you know, what happened when and which way was it moving? So I am talking about the Northern Highlands terrain, which is this area here that you can see on the map. It is bounded by the Moyne Thrust over in the west and the Great Glen Fault over in the east. Those are the two main thrusts here. Can you guys see my pointer? Yeah, so this is the Moyne here, and then the Great Glen Fault, which is a massive fault. And then everything in the middle there is the Northern Highlands terrain. It's composed primarily of metasedimentary rock, which was all deposited into much, much older Lewisian gneisses. The sediments were deposited around 900, maybe 1,000 to 870 million years ago. And then there were two different major orogenic events. The first being the Neodartian, which is about 870 to 720 million years ago. And then the second is the Caledonian orogeny, which is 480 to 400 million years ago. The Caledonian currently is divided into the Grampian and Scandian events, but likely there was some stuff happening in between those two events, and I'll kind of talk about those in a little bit. So what do we know currently about the tectonic transport history and the timing of that in the Northern Highlands terrain? So in a paper completed in 2021, we published that quartz fabrics just inside of a rock, quartz which got smushed and then pushed in a certain direction. Those patterns were showing that tectonic transport directions changed over time. Early on, they were moving in this kind of northwest pattern, and then as we move to the west, we have rocks that are much later being moved to the west northwest. So all of this was happening though in the Caledonian. So this is all a much later orogenic event. Things were all being pushed together, and we see this, yes, in this particular area, but in plenty of other places to the north. The problem is that most of the research that follows along with the paper that I was just talking about is doing all of its work up in the northern half of the Northern Highlands terrain. So it's this like darker red area up here. People have published a whole lot of papers on the tectonic motion, the temperature pressure changes, and then the ages of the deformation itself, which we've used to kind of piece together, okay, well, what in general is happening in the entirety of northwestern Scotland? And for the most part, it seems to work, except that this whole area that's in orange, most pretty much south of Inverness, has like maybe a couple of studies done on it, but some of those studies might be suggesting that we are getting transport directions that are a little bit different than what we see in the north, and some timing that might be a little bit different than what we see in the north. So it's not necessarily true that we're having the exact same story happening in both of those locations. They're definitely related, but which one happened when is what the question is. So my research area is in the southern part of the Northern Highlands terrain. This map is showing generally the extent of where we were working. We have the same major faults, the Moyne Thrust over in the west and the Great Glen Fault over in the east. But then we also have one more major fault that we've added, which is the Scurbag Thrust, which is this big kind of long folded line that cuts through my map in a couple places. Scurbag Thrust is probably a much older thrust, but we're wondering, okay, well, was there some sort of tectonic motion that was happening, and can we see it now? The units that are present are the Mora group, the Glenfinnan group, the Loch Eel group, and then we also do see some of that Lewisian, really old, nice kind of popping up here and there. The other thing that's important for at least this talk is that we split the entire area into two kind of structural regions. One is the steep belt and one is a flat belt, and then this Loch Quick line, which is this dotted dash line that kind of crosses in between, is the imaginary line that cuts those two things in half. The steep belt has steeply dipping rocks. A lot of the rocks are almost vertical when you're looking at them in the field. The flat belt, on the other hand, are flat. We're not really creative with the naming, but it did make the steep belt was a whole lot easier to get rocks from than the flat belt, because most of the stuff in the flat belt is covered by grass or people were living there. So this here shows the transects that we had and then kind of our sampling area in the flat belt. So 1, 2, 3, and 4 are all sections that are in the steep belt. They are all transects that are crossing that Scurbag thrust that I was talking about earlier. We were definitely kind of limited based on where we could reach. So I'm sure that many of you have driven up there. There's very few roads. So we were trying to find some spots where we could go there, and then hopefully people in the future could kind of go back and easily access these rocks. So that's those locations. And then we also have a couple samples that are picked up in the flat belt, which is that big kind of orange blob over there on the right side of the screen. Okay, so first part of the project was looking at deformation and shearing directions. Both of these pictures were taken from some of our field locations. We had very, very nice weather when we went out, which was very strange. So we were really lucky. We were able to pick up a whole bunch of samples. When we collect these samples, we make sure that we know, that the samples are oriented properly so that we know which way, they're striking, which way they're dipping, so that when we bring them back here, especially since we're coming all the way back to the US, that we know what we were picking up and what we were looking at. So we collected samples from those transects that I showed you a bit ago. We made sure that all of them were labeled, and then we came back, we cut them into thin sections, and then we're going to do microstructural analysis. And what I mean by that is we're looking at the grains inside of the rock. I am taking the rocks, making thin section out of it, putting it underneath my microscope, and then we're measuring the grain sizes. Primarily, we're doing all of our analyses using quartz, because quartz is easy to find, but also it's really easy to measure. So out of that, we can get the crystal fabrics, which is what tells us, okay, we have a rock, it's being sheared, which way are our quartz grains recrystallizing, which way are our grains leaning, and then that can tell us the directions. But we were also trying to measure the size distribution of these grains to figure out, okay, do we have motion happening on the skerbeg, which is much older motion, or are we seeing motion that's happening all over the area that's about the same? For the next couple of slides, I'm going to go over two of our collection sites. I'm going to talk about the flat belt samples, and I'm going to talk about Kinloch Corn. Otherwise, we're going to be here all day long. So this is a flat belt. Some of our samples were collected from this location. This is from a little spot kind of hidden in there. So the shear sense in the flat belt. The flat belt, we found shear senses going north-northwest, which, if you remember from a couple slides ago, is very, very similar to what we're seeing up in the northern half of the Northern Highlands terrain. We see that grain sizes are generally consistent through the flat belt. There aren't any big grain size changes, whether we're sitting next to the Great Glen Fault or as we go closer and closer to that Loch Quake line. And then we're seeing a deformation temperature ranging from 550 to 650 degrees Celsius. Just a note for the next couple slides, you're going to see a couple of these block diagrams, and that's just to kind of help visualize which way the rock was moving. So if I say that something is moving top up to the northwest, it's as if the top of the rock is moving towards the northwest, being pushed from the back. All right, so now the steep belt. Steep belt, I'm doing just one of the transects. All the other transects are pretty much the same. So this picture is from Kinloch Corn. So using Loch Corn as an example, we were seeing continuously a south-southeast shearing, where the top of the rock was essentially going backwards. Grain sizes were not decreasing across the skerbeg thrust, which was something that we were trying to figure out, do we have motion skerbeg thrust or not? Since we don't see decreasing grain sizes on the skerbeg thrust, or as we're getting closer and closer to skerbeg thrust, that's suggesting that this is a much larger deformation event. And then we saw deformation temperatures from about 610 to 500 degrees Celsius, decreasing from the hanging wall to the footwall. So what does that kind of look like in the entire area? We see generally top to the southeast direction, so everything's moving kind of backwards in the south. Oh dear, I have my figures flipped, sorry. This figure right here is supposed to be going to this side. So we have this top kind of backwards motion in the south near the steep belt, and then we have this top to the northwest motion over in the flat belt, my apologies. And then weirdly enough at Loch Monar, we get a slightly different shear sense. If we have a top to the southwest, we're still trying to figure out what exactly that is. It could be that this entire area has this weird little fold that goes through it, but we're still trying to figure that out. So we have all of these shear senses, but it seems that many of the shear senses in the south are opposing the shear senses that we've seen continuously in the north. So like I said, north-northwest motion in the flat belt, which is really similar to the stuff that the senses of motion that we see in the northern half of the Northern Highlands terrain, and then a south-southeast motion in the steep belt pretty continuously along all of my transects, and we're pretty sure we're seeing them a little further south in some samples that got collected later. But this really leads to the question of, did the southeast motion occur before or after the north-northwest motion? So kind of going back to, we have two different orogenic events that happened: Neodymium, which is really, really old, and then the Caledonian, which is much more recent. So the only way to do that is to get radiometric ages out of our rocks and then try to tie them together with the deformation that we see. So how did I do this? This is kind of what I've been doing for the last year, using the samples that we collected. We gathered uranium lead dates from 3 different kinds of mineral: titanite, monazite, and xenotime. If you haven't heard of some of those, that's okay. I haven't heard of them until this year as well. These are really cool minerals in that they will keep uranium when they first grow. And then, of course, uranium decays over time, and we can get a general age of when metamorphism was happening. So we did try, when we were selecting samples to get dated, we only got 10 of them dated. We tried to get 2 samples from each of the transects, and then 2 samples from that flat belt region. Then we took these really nice pictures of them using the electron microprobe over at Virginia Tech. And then once we figured out what grains that we wanted to use, titanite, monazite, and xenotime, I went ahead and got these really nice grain maps done, which partially worked really well for the research side of things, but also worked really well in that we got really fantastic pictures. After that, I flew to the other side of the US to Arizona and got the grains dated. And since then, we have been trying to figure out, okay, when did things happen? And then what can we tie to the deformation that we see? So these are the locations that these are the samples that we ended up getting dated. All the dots that are in blue right here, these are titanites. The orange dots are monazites, monazites xenotime as well. And then this one spot right here happens to have both monazite and titanite in the exact same sample, which we thought would be useful just in case we were getting a certain age population of monazites, a certain age population of titanites. Could we tie those 2 things together? I mentioned those microprobe maps of the grains. For those of you who are interested, these are yttrium maps. We found that all the grains kind of throughout titanites and monazites, we see yttrium zoning. Monazites and titanites seem to flip, so that in monazites we have cores of high yttrium, and then in rims you have very little yttrium. In the titanites, we have the opposite, where we have cores of very low yttrium, and then a rim that starts with high yttrium and kind of fades away. We did have a couple samples that were a little strange, and at first we thought, okay, maybe this is like a tridal grain, so this is something that got deposited a long time ago and just never got, recrystallized. But kind of as we looked through it and looked at the elements that we were seeing, and also just generally what did the rock look like, we found that there were probably just a lot of fluids that were going through these rocks. So these are our ages. Here are the flat belt ages. The circles that are in orange, those are monazite ages. The circles that are in blue are titanite ages. All that you guys really need to get from these plots is that we are seeing 2 different age populations. This is 2 different samples that got dated. So this is FB2 and then FB11. We were seeing a younger kind of Caledonian age, which is 442 to 420 million years. And then we were also seeing older, kind of slightly younger than Neodymium, but almost Neodymium age of 689 to 682. Something else that's interesting, and we were able to see this in the flat belt, but we also saw it in some others, is that with the zones of our titanites, and we also see this in the monazites, is that we have in the core these older ages, and then on the rims, kind of like here and these spots here, these are our younger ages, which we can use to figure out, okay, when specific events were happening. Looks like we did indeed have a pause in this metamorphic growth from one period to another. Similar thing happening in the steep belt. So this is once again looking at Kinlochhorn samples. Kinlochhorn only had monazites in the samples that we got. We looked and looked for titanites. We could not find any. So same kind of thing, though we're seeing two different populations. A younger population, 435-ish, that's more Caledonian. A much older population, which is that Neuydartian 743, 742-ish, that's perfectly acceptable. And then once again, we see this 686, 89 time frame, once again coming from the cores. Another thing that was kind of neat that we found in the monazite specifically, for those of you who are interested in garnet, we had a number of garnets that had monazite sitting inside of them. And that's very nice for us because that means that the date of that monazite is set, unlikely that it's going to get messed up through, liquids coming through and removing monazite. And then all of those were giving, or like all those monazites that were sitting in garnets, we were definitely getting that 740, 742 million year age. So this is the overview of ages, and it's a lot to look at all at once. But generally, we're seeing a Caledonian age event, a Neuydartian age event, and then you'll see it in a second, but these just younger than Neuydartian events popping up. Ages do not seem to follow any specific geographic or lithologic unit, so this is something that is happening as a pervasive metamorphism, pervasive deformation all the way through the southern northern highlands terrain. Caledonian and Neuydartian ages are occurring on both sides of the Skirtbeg thrust, so it does not seem that we're having specific motion occurring just in the Moyne, or kind of to the west of the Skirtbeg, or specific ages are popping up in the flat belt. But the only thing to take away is that we do see as kind of like a spatial pattern is that the flat belt samples and one sample from Kinloch Horn all have that 680 something year event. So this is what that looks laid out. So it's a little easier to see. Like I said, we have a lot of Caledonian ages, we have some Neuydartian ages, and then we have this little blip of something happening just after the Neuydartian. All the stuff in this gray box, this darker gray box on the bottom, those are all ages that were previously published. And just to show where our ages are in comparison with their ages. Something I would like to note for at least how we did our dating methods is that we're going to have slightly bigger uncertainties because we were getting all of our grains dated in situ. So we primarily have Caledonian ages, but this brings up a really big question for those of us who are looking at Caledonian origin. Of course, Neuydartian brings up a whole bunch of things to talk about, but Caledonian, just to focus on, is the Caledonian gap. Right now, we have the Caledonian kind of separated into two orogenies with a gap of time in between those two things. So we have the Grampian and then we have the Scandian events. Well, if you're looking at my dates, and even if you look at the dates that were previously published, you can see that there's quite a few dates that are landing in this gap right here. There is no name for it, but we have seen continuously both my samples. I was talking to another grad student who's doing a very similar project to this one. Many of her samples are landing kind of in that in-between space in the Caledonian. We know, at least from this, is that the Skirtbeg thrust definitely was not moving in the Caledonian, at least not in this particular area. So most of our stuff was either really, really old grains that we were getting from Neuydartian deformation, Neuydartian metamorphism. And then we got this period that probably grew over a lot of the older stuff of Caledonian growth. The next thing that we have to figure out is what do we want to call this period? And then hopefully me or whoever else I'm working with can try to piece that together. Anyways, that's all I have for you guys for now. I know it's a lot, but it has been a really fantastic project to work on, and many, many thanks for the funding, because that got us out into the field and we did like a month of field work, which was pretty fun. Yeah.
Thank you. Thank you. We'll have questions at the end, but thanks very much for that. That was very, very interesting. So now we'll go to, sorry, glasses, Kiara. Kiara's from Exeter University School of Mining, and her talk is on the paragenic evolution of tin-dominated lode systems in the Poole Mining District in Cornwall. So over to you, Kiara.
Thanks for the lovely introduction. I'll share my screen. Hopefully you can all see this, yeah. Perfect. Grand. Yeah, I'm conducting the large-scale reassessment of the tin, tungsten, copper ore field in southwest England. And I work with 4 mining companies down here, and I'm just going to focus specifically on the Poole Mining District because we have a nice story developed there. So that's what I'll talk to today. This one. Perfect. So southwest England, down here in this lovely peninsula, not as sunny as you guys up there, unfortunately, today. But we have some amazing geology. And it comprises of this Devonian, Carboniferous, sedimentary and volcanic successions that were deformed during the Verskyn orogeny, during which this 10-kilometre thick granite batholith, which you can see are these red big splodges here on this map, formed and were constructed over a 20 million year period in the early Permian, which was an extensional tectonic regime. So the mineralization here was primarily controlled by these steeply dipping extensional fault systems, very much related to the granites, in which mixing between the magmatic hydrothermal fluids and the meteoric fluids took place. And this is where we get our principal ore systems of wolframite, cassiterite, and chalcopyrite seen. And then we do have this later stage of extension, which produces these cross-course vein systems and fractures cross-cutting the granite, hence they're cross-course, and these are these north-south, deeply different one. And you can see here that the oil field is very much related to the granites. We have the cassiterite mineralisation centralised within the granites itself, and then we have more roundabout are copper-dominated. So if we zoom in on this picture here, I collaborate with 4 of the mining companies. So we have Cornish Tin, which is South Crofty, and that's where we're focusing today on this Poole Mining District, which was, you can see, a hub for minerals and ore deposits here. We've also got Cornish Lithium, which is nearby, and they're looking at more the lithium granites, but again, he intercepts these mineralized vein systems, and we're able to get a full spread. And then we've got Cornish Tin down the bottom here in that Wheelvore mine, which is really big in its day for its tin, cassiterite. And then all the way up here is a thin copper system in sheeted veins with Cornwall resources. So we've got a nice spread around Cornwall, and because there's been like recent heyday in drilling, here we're getting new core, new data. So it's a great time to be here. So historically, as I say, Cornwall was a hub for its mining activities. So at its peak, it produced around 50% of the world's tin and copper. And then, unfortunately, all mining research and activities stopped in 1998 after the pin price crash. But as shown by this timeline that I've drawn up of the Poole Mining District, you can see that there's been continued exploration and development here, with the underground mine is planned to be rescheduled to open in 2027, which is really exciting for everyone, and loads of people are quite happy to see that. And so there's been a lot of diamond drilling, kind of reassess this resource, and across Cornwall. So there's been more diamond drilling occurring in Cornwall over the last 5 years than there has ever been. So my PhD aims to bridge this 30-year hiatus by using new analytical techniques that hasn't been used before and going after core that's deeper than they've ever had. So it's kind of like a big overhaul reassessment of the area. So Farmer in 1991 did the most detailed study of South Crofty, and that was over 30 years ago. So he split the tin bearing lode systems into two main groups based on the geology, and they have two clear fluid chemistry. So first we see this blue tourmaline considerate vein system cross-cutting the black tourmaline breccias, and their fluid chemistry plots here, and we have this lovely range of salinities and temperatures. It's really big with this narrow salinity range. And then we have, on contrasting, we have this chlorite, fluorite quartz with cassiterite seams brecciated in between. So these are the cassiterite minerals here, still lovely, but they're more associated with the gangue. And then we see that the temperature range of these fluids are a bit smaller, but we have this wider salinity. So we have two very different systems. And also to note, with the chlorite stage, we've seen, oh, sorry, I thought there was a wee graphic there, but there's not. The chlorite stage, we see this mixing with the meteor fluids and basinal brines. There's this general mixing trend occurring between all three. And that's what his data found out from the South Property Mine. I'm using this as like a comparative study to see what my data will show you. So we'll come back to this later. So the principal lode systems with the Pool Mining District are seen here in yellow. And I conducted detailed logging of these, of 8 of these, which you can see some of them are in red. And I collected over 100 samples from the diamond drill core, which reached depths of over 11,000 meters, or 1,100 meters. And this data led to this pyrogenesis table. So down here we have the main lode systems that I've looked at, and you can see that there's 6 main pyrogenic events that occurred within the area, and each lode had a varying amount of each one, or not at all in some cases. And then what we see here is that the cassiterite in this grey colour occurs both at the start and the end of the tourmaline mineralisation, which remember from Farmer, he said that there was very much of a link between tourmaline and cassiterite. And what we're seeing here is something a wee bit different, that it's actually in trilogy-wise either at the start or the end, so it's not overly linked. And then we are seeing that we have these multiple generations of tourmaline occurring. And we've got tourmaline veins, tourmaline breccias, and we might see a vein system brecciated, or a breccia by a later vein, and we've got blue and we've got black tourmaline. So a lot of stuff is happening, and we try to unpick this. So to show you some rocks, that's why we're doing geology, isn't it? This is what the earliest stage of mineralisation is, and it's called a quartz feldspar floor. So these came off the granite, it's very early stage. And what you can see here is that we have our quartz floor at this end of this core system. I hope you can all see my cursor. And then we've got this lovely blue tourmaline breccia that has brecciated it. And this section images come from that. You can see that this quartz is formed lovely and early and cross-cut by this breccia system. And we see these early quartz fluorite floors in a lot of cases. We've got our feldspar occurring, it's cut by some our quartz floors, we've got our tourmaline breccia systems, and a lovely cross course being cutting through everything. And again, we can see this here. We've got some more feldspar quartz floors forming these lovely lines, tourmaline breccias. And we see this in numerous occasions where the tourmaline breccias do like to follow these early stage vein systems. Just easy fluid flow. Then we've got our tourmaline veins and breccias. So we can see that we've got these lovely dark vein systems that cross-cut the rocks, they brecciate it, and we only really see residual quartz within this. We might see some relic granites, but on the rare occasions, so there's some nice brightenized granites in there. But it just like sublitate everything and sort of like completely override. So when we do see later stage alterations, like here with the hematite and the chlorite, it's definitely away from the vein systems because it just can't permeate this tourmaline. And I know when I made the thin sections for these, they were really hard to do because of how hard the tourmaline had become. They were just so fine grained. It was a pain. Would not recommend. Yeah, you can see that we've had multiple different iterations, and it just cross-cuts everything. And then we have our visible cassiterite, and this is what everyone's looking for. This is where the hubba is. What we see is that we've got these cassiterite veins cross-cutting our tourmaline breccia. And you can see it lovely here. Here's our lovely cassiterite veins, and this one's infilled with fluorite. And then same here, we've got our tourmaline vein breccia, cutting everything, and a lovely cassiterite fluorite vein. Here is just massive cassiterite. It was very anomalous because it was found on the hanging wall of a tourmaline altered elven. So, and I will explain more about why that is later. And then this is in some of the other lode systems here. We've got Dulcos lode, and again, we see the cassiterite veins occurring as like little veinlets throughout the tourmaline breccia, more associated with the tourmaline now, but still quite small. And then we've got a tourmaline cassiterite vein here in our intermediate lode, it's called, but we're also seeing a fluorite cassiterite vein. So it shows that tourmaline and cassiterite not always associated, but we're seeing cassiterite to multiple different phases everywhere. Yeah, so we either see a cassiterite occurring with no clear vein boundaries and as massive cassiterites, which is this lovely guy down here, or within vein systems cross-cutting our tourmaline breccia. And those are two main cases. And then we've also got our sulfides, not as prominent within the Great Flat lodes, but they do occur and they are late stage. So they come in the infill where they can. And mainly chalcopyrite or pyrite is their thing. And then lastly, we have this quartz chlorite vein system, also probably our cross course. It's just hard to tell when they're in core system. And you can see that these, when they come, they're very pervasive alteration. We have huge alteration halos associated with them. And they too like to just obliterate everything and remove all textures. So if we focus on the Great Flat Lode, and we look at our Quenska mineralogy, here I have a sample of a vein dominated cassiterite, and you can see the cassiterite and the fluorite are nice in association with one another. And then we see that we have 35% of the cassiterite is associated with tourmaline, but all of that percentage is along this vein boundary here, where there's not really much tourmaline occurring in with the cassiterite itself. And when we look at our massive cassiterite sample, we see that we have this ground mass of quartz, Fe oxide, muscovite, tourmaline. So it's a very different assemblage to what we're seeing the vein systems in. And as a comparison, I put through just a tourmaline breccia to see if there was any cassiterite we weren't picking up on, and there's nothing. There's 0% cassiterite within that tourmaline breccia, which was quite interesting to see. And we do have quartz tourmaline veins cutting through and some quartz pyrite veins, but no cassiterite. We take this sample and we have a look at those cassiterites, and it gives you this lovely image under cathodoluminescence. So this is when you hit the rock with a high electron beam, and it gives the growth structures of a mineral. And it's stunning because you can see how it's grown. What we see is we've had the first stage of growth, then we've had this second phase where we've had a dissolution textures eaten away at the mineral. And then reprecipitated more cassiterite of a different chemistry. So within our LA ICP-MS mapping, we can see that these are very tungsten poor, Fe poor assemblages. They're shown in black here. And then we return back to our mineral growth, and then a very linear stage. So we've had precipitation and reprecipitation. And so further analysis on this sample was conducted through microthermometry, which also shows similar events. So this sample is anomalous because it contains CO2 in the form of clathrate, which if anyone's done fluid inclusions out there, they'll know that if you encounter CO2 as your first inclusion, that's not a fun time to do, especially when you're expecting the be-all end-all, like just salinity fluids, like you've been taught and you're left with this. It's not great. So that was quite fun. But we do see this cluster of high temperature, high salinity fluids. They're plotting really high here. And this is from our cassiterite. And then we also have some fluid chemistry within the mineral itself. I've put these, and these are the zone bandings that you can see. And I put them in order from the closest to the core to the furthest. And what you can see here is that we have a temperature that drops down as we move away from the rim and then shoots back up, back to the end. So this shows that there's been a rejuvenation in our fluids. And although it might be linked to a change in the pressure system, we don't think so, because all of these vein systems do occur quite close to the top. So we've had the fluid cooling and rejuvenation stage. And then I did this little quartz vein that was cross-cutting through to see what that was doing, and that again contained clathrate CO2. It had a long scale, so we're seeing this large temperature homogenization range and a narrow salinity, indicating again that we've had fluid cooling through this. And these in here were primary fluids of different populations throughout, so I know that they're not net or leaked or they're giving me false results. Which is key to know. So we've had, again, fluid cooling and reprecipitation. So it just shows we've had this rejuvenation. And then if we look at our vein system, which shows a little bit of a different story under CL light. This mineral is taken here, and you can see that we've had this regular growth of the mineral spanning outwards. And then we have two cross-cutting cassiterite events where we've reprecipitated our cassiterite mineralisation. So this section here has been faulted by number 3. And you can really see this, and this is the plane polarized and cross-polarized there, like there. So you really see the detail that you're missing within your plane and polarized. And then if we look at our laser ablation data, we can see sort of a similar thing where the cross-cutting vein systems are really high, rich in tungsten and iron, which is very anomalous for the area. And we see that we've had this lovely growth texture as well occurring. So we look at this vein system. So this is what I've been showing you. It was in here. I took 2 samples from this, 10 and 9, and then I took 1 sample from Dolco Load, which had fluorite in it for fluid inclusion analysis. And what we see is that our cassiterites plot quite high in their temperature but lower in the salinity range. And then we have our fluorites, which plot in the moderate salinity, lower homogenization temperatures, and we're seeing this long range again, and which indicates we've had a presence of fluid cooling. Now we've also got the presence of meteoritic fluids, both as primary and as secondary inclusions. We've had a bit of fluid mixing coming in, and you can see this because we've had a little bit of trail into the fluids downwards. And then within the fluorite especially, we've had this like high salinity, low temperature cross-course fluids come in. And these are all secondary structures within a separate little veinlet that was in it. So it's interesting to note that we're seeing that, so they're following the same fluid pathways. So if we compare, so I've put all of the samples that I've done to date on the Crofty system here, and what we see is we've got a quartz tourmaline vein, which is this one here. We've got a quartz chlorite vein, and then we've got our 9 and our 10, which was our cassiterite within the vein systems. We've got our massive cassiterite, and then we've got the Dolco cassiterite vein. And this is all the primary data for that. And what we see is that our massive cassiterites, they plot well outside the range of our vein cassiterites, which plot here. And then we have our meteoric fluids, and this becomes heavier in density with the addition of the quartz, tourmaline quartz chlorite vein system. And we see this meteoric mixing still. And the only one we've seen cross-course fluids is in that fluorite cassiterite vein systems. And we have seen, you can see here, that we've got fluid mixing between our meteoric fluids and our cross-course fluids. These little ones here that sort of span both look like they're mixing in between. So I compare the primary to what Farmer did in 1991. What you can see is that the massive cassiterite vein systems really plot out with any of his data sets. This is really anomalous. And then we mainly plot in the chlorite stage. Although our geology is quite different, we plot within there. And we do have this mixing that he's seen, albeit not as much, with the meteoric fluids, but it is occurring within those samples. You can see it sort of trailing down. It may look like there's mixing in between the abrasional brines and the cassiterites, but these trends are more linear than they are diagonal when you look at them. And so that's why that might appear the way it is. And yeah, so I think that we've got this like really anomalous CO2 which he did not see. So that probably indicates the presence of like a deeper mafic system, or the incorporation of the peelites themselves within that cassiterite system. So as a conclusion, we've seen cassiterite formed through several different fluid pulses, with the fluid undergoing cooling and regeneration each time. And the cassiterites within our veins post-date the cassiterite breccia itself, which is a bit contradictory to the historical literature. This could just be because we're looking at a deeper hosted vein systems. And we do have mixing between the magmatic hydrothermal and meteoric fluids. And then we have the massive cassiterite mineralisation, which is probably linked to CO2, which has CO2, which is at higher temperature, higher salinity, and it's formed on this hanging wall igneous structure, which is probably linked to a presence of deeper systems. So that's all I have for you today as well. Thank you. Oh, and of course, thanks to all my project partners, especially Cornish Metals, for helping with this project.
Right, thank you very much. That's very good. Now, if anybody's got